Good morning. You all can hear me? Yes? Okay, good. Um, so today is lecture 17 in which we start probability. So I just wanted to know if you guys had any questions about the previous work. Remember, yesterday I was happy a bunch of people came to see me and I hope I helped them a little bit. So that's great. I was very happy about that. Um, so let's see. I won't quite start. I'll remind you once again that the pre-recorded videos now are just optional, although recommended, at least for going over some of the example problems or the practice problems, because I think that it gives you a broader, you've seen more of the same kind of problems, so it's easier for you to recognize how to solve them, I think. It's not that it's different material, it's just, the same way when you practice a language, the more you practice conversations, the more you recognize and are more easily able to understand other people. The pre-lecture quizzes are now not due before lecture. They're due the morning after lecture at 11 a.m. Okay. I tried to put up most of the rest of the semester so you could see where it's going. You won't have access to the pre-lecture quizzes until, the standard times, not post-lecture quizzes, problem sets until the standard times, but you can do whatever you want with looking at the videos and see what's coming up. I remind you the last class is the 27th of April. That's this month, as far as I know. And our final exam is the 30th, the Friday. So it's only a few days later. If any of you have looked up this material and think you have a different date, please tell me. I could make a mistake. I'd like to know because I don't want to make a mistake and change anything from what the university says we should be doing. Okay? Good. So let's launch in and ask questions. Well, what is probability anyway? Okay. So in chapter 5, we talked about how do we answer the question of how many? Okay. So we asked the question of how many, but we didn't ask the question, for example, that says, well, how many out of how many possible? So sometimes, for example, if we roll the dice 3 times, okay, then we're creating an ordered triple of letters, an ordered list that allows repetition because we can get a 1 to 6 on either one. But if I ask you, how many 7s can I roll? Okay, that answers the question of how many 7s. But when we want to know probability, we're asking the question, for example, of how many 7s can I roll out of all possible triples of rolls, ordered triples of rolls, okay? And that gives us effectively a percentage. And that percentage is called the probability, okay? So let's launch into the right terms that are used in this chapter and how we go about doing work with them. So one of the things I think you maybe in your youth, because you don't have time now, saw the show Let's Make a Deal. And Monty Hall used to be the host of that, the MC of that show. So what was Let's Make a Deal? Well, for the winner of the standard stuff and the deals, they would have 3 doors, and behind the doors, they would have 1 great prize and 2 booby prizes, so to speak. So here's an example of it. Behind 1 door is a new car. Behind the other 2 doors is a lifetime supply of car wax. So obviously the car wax isn't great if you don't get the new car. So you're asked, you pick a door. Okay. And that's the door you pick, and you have, 1 out of 3 choices. Say that's called 1/3 probability of having picked the right door. But instead of opening your door to tell you if you won or not, Monty opens one of the other doors, not one of the ones you picked, and says, you can change your mind. Okay, you can pick the other closed door or stick with your choice. What's your best strategy? Does it make a difference? What's the probability that you will win? Okay, what's the percentage? Okay, so this is a problem that everybody gets wrong. Okay, not everybody, most people. Why? Because it doesn't seem to make any difference. You sort of say, well, I had a 1/3 choice of winning. I now know that one of the other doors was not the right thing, but why don't I just stick with what I have? Okay. And the Monty Hall problem is telling you that the answer isn't what you think. Okay. And I'm not going to go through the solution right now. You can look it up online, or we can talk about it at the end of class if there's time. All right. So that's a classic problem. And it's a classic problem because it's so non-intuitive. So what we're going to start learning about are how do we compute, not this problem, this is more abstract than that, although we will talk eventually about the solution. So we're going to start out and ask the simplest questions and try and get a grasp about what probability means for those simple ones, and then build up to more complex answers. Okay, so when you talk about probability, you have to talk about the sample space. What are the set of all possibilities? Because you can't decide what percentage you're asking about if you don't know what it is. So in the case of rolling 3 dice, for example, we have 6 choices for the rolling 1 die 3 times. We have 6 choices for the first roll, 6 choices for the second roll, 6 choices for the third roll. And we learned last chapter that that's an ordered list with repetition allowed. And so the number of possible outcomes would be 6 times 6 times 6. The number of choices for the first solution times the number of possibilities for the second solution times the number of possibilities for the third solution. Okay, so we have 6 times 36 or 198, whatever, solutions. Okay, we assume the likelihood is known. For example, if I'm rolling that die and it's a fair die, that means each side is equally likely. It's not tilted so that one side would come up more. That's perhaps easier to understand when you think about tossing a coin. If the coin is evenly weighted and appropriately minted, then either side can come up an equal number of times. Now, when people talk about an equal number of times, they don't mean that when you toss it twice, you're going to get 1 head and 1 tail. What they mean is if you do a long enough set of tossing, okay, what's long enough? A lot. Then eventually you'll see that half the time it comes up heads and half the time it comes up tails, okay? But if you have a weighted coin, a biased coin, then one side will come up more often than the other. And when we talk about coin tossing, never think about the fact that it can come out on edge. That one we're not discussing. It's too hard. So what we have are 2 choices, but when it's biased, one side will come up more often than the other. Okay? So then it's not equal possibilities, because we know, for example, if it's biased towards heads, that in the long time, if we roll them enough times or toss the coin enough times, that the heads might come up, say, 60% of the time, and the tails might come up only 40% of the time. So they're not equally likely outcomes. So we'll start with the notion of equally likely outcomes. And then later in the chapter, we'll talk about what happens when they're not equally likely. Okay, so an event is the subset of all possible samples that have certain properties. So in our case of rolling the dice 3 times, the single die 3 times, okay, we can ask what is the possible things? How many times out of the total will I roll? Is the possibility of rolling, let's say, 2 4s? Or I can say at least 2 4s. Okay, so that would be an event. Okay, so an event is a set of possibilities. Okay, so we say if a single event is equally likely, then the ordered tuples of those events are equally likely. So for example, if I say that rolling the dice, any one of them is equally likely, then you say the ordered tuples are equally likely, but that's not always true of subsets, okay? That's not always the case. So here's an example. We roll 2 dice, not 1, and we look at the set of outcomes as the sum of the values. Are all those values equally likely? I see some head shaking. Thank goodness I have a picture of people. Good. So no, I can only roll a 2 one way, is if I get a 1 on one die and a 1 on the other die. Okay. But I can roll a 7 lots of ways. I can roll, I can get, say this is my first die and that's my second die. I can get a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. So I get 6 different ways I can roll a 7. So a 7 is much more likely to be rolled than a 2. Okay. So on the other hand, suppose instead of looking at the sum of the face values of the 2 dice, I asked, well, what can I do so I break the space up into equally likely rolls? And the way we do that is we say, well, look at each die and think of them as an ordered pair. Okay, so we have the ordered pair so that, let's say I have 1 red die and 1 blue die. That's easier to see them as an ordered pair. And I put the red die first and the blue die second. So then a 1 and a 6 is not the same thing as a 6 and a 1, because which color comes up, which number comes up is ordered by which die it's on. Okay, so now I can only roll a 6 and a 1 one way, and I can only roll a 1 and a 6 one way. So in that case, if I look at them as ordered pairs, and my dice are fair, all of the possibilities. How many possibilities are there? Well, remember when we talked about sets. When we talked about sets, we learned that I have a set. If I have a set A, and that consists, let's say, of 1, 2, 3, 4, 5, 6. This is back to chapter 4 now. If I had a set A, and I think about that, and I'm looking at A cross A. Well, A cross A, remember, is the set of all pairs I comma J, where I and J are both in A. And if we count it out, and what we learned in chapter 4 was that it's equal to the number of elements in A, and in this case, times the number of elements in A. So if I have 2 sets that don't have the same numbers, I still can use that, and that's equal to the number of elements in A cross A. Good. Well, here, when I look at this, I'm looking at the rolls of the die as an ordered pair. And so they're equally likely, and each of the elements comes from the set A, namely 1, 2, 3, 4, 5, 6, equally likely on that. So how many choices do I have? Well, I have 36 things that are equally likely. So the possibility is 1 out of 36, or 1/36. Okay, so that's the difference between equally likely. So you have to be careful when you specify what are the outcomes, what are my sample space, and what am I calling the events. Those are three things that will decide how you solve problems of asking what is the probability, or another way, what is the percentage? Okay, good. So here we go. Given a finite sample space S, in the case of our rolling two dice, that sample space is going to be the set of ordered pairs of what my rolls can be. It has n of S outcomes and an event E. Remember, E is a subset of what you're calling successful outcomes. Then probability of event E is equal to the number of elements of E divided by the number of elements in your sample space. That's why it's critical that you call your sample, figure out your sample space properly in order to get this right. So here we have, what's the probability of rolling a sum 2 on a fair pair of six-sided die? Well, there's only one way. Think about our pairs, and I have 1 and 1 is the only way. 1 and 1 is the only way I can roll a 2. Okay, so n of E, that's the event, is 1, and n of S is 36. So the probability of rolling a 2 is equal to 1 over 36. Excuse me. Okay, does that make sense? Good, keep going. Let's do a practice problem here. All right, so our experiment is to toss a fair coin 5 successive times. So before I do anything else, what will our sample space of equally likely outcomes look like? Well, if I toss it once, what's my sample space of outcomes? Well, I can get a head or a tail. So that's going to be my set A. So what is my space? What are my sample space of outcomes? Well, it's equal to all 5 tuples. Let me say, call it A1, A2, A3, A4, A5, such that A sub I is in the set capital A for I equal 1 to 5. Does that make sense to you? When we were counting in chapter 5, we did that all the time. Okay, so what is n of S? Well, remember, we just said when we're looking at tuples like this, at all tuples like that, it's equal to the number of elements in the first set times the number of elements in the second set times the number of elements in the third times the number of elements in the fourth times the number of elements in the fifth. So how many elements do I have in the first set?
By the first set.
2, right? And there's 2 in the second, 2 in the third. So what we have is 2 to the 5th elements in our sample space. Okay, so now that's our set of equally likely outcomes. This is it. Now, how do I write E in terms of S? What is E? It's the event that the last 2 tosses have the same result. So what are the last 2 possibilities for the last 2 tosses? what we're looking at is something that looks like, anyone want to take a guess before I do it?
Would it be two? Yeah, you only have heads, both heads or both tails, but then you still have to pick the first three outcomes before it. So 2 to the third times 2. So 2 to the fourth.
No one wants to take a guess? Dane, oh, okay. Now you have you're muted again. Okay. Well, what we do is we look at that and say, well, what does it mean to have the last two rolls be the same? So it means we have no idea what happens. Sorry. We have no idea what happens on the first three rolls, but the last two rolls are either both heads or the last two rolls are both tails. Can it be anything else? So our sample space E is the set of all rolls. What do we call it? E is the set of all rolls. So it's the set of all R in S such that R sub 4 equals R sub 5. The roll for the fourth equals the roll for the fifth. And each of those is either in the set head or tails. David, yes.
Can you hear us?
No question? You have your hand up. What's your question?
You can't hear us.
Is my audio not on? Oh, wow. You mean no one's heard anything I've said?
No, we can hear you. You just can't hear us.
Oh, thank you for raising your hand. Now, what are your questions? I'm back on. I'll go backwards. I apologize.
Oh no, I just know Dane totally gave a great explanation of exactly what you're asking for, and then I noticed that you probably couldn't hear us.
I couldn't, but I really appreciate it. Thank you, Dane. So the next time that happens, wave your hands or do something. I usually don't do that, I don't think. So yeah, you did say that. You can hear me, but I couldn't hear you. I apologize. Wow. Thank you, everybody, for seeing that. And I appreciate that you gave an answer, even if I couldn't hear it and the rest of you could. Okay, so we have E, our sample space. So what is the probability of E? Well, how many elements are in E? What is N of E? So how many possibilities do we have for the first three? We have 2 to the 8th possibilities for the first three. And then how many possibilities do I have for the last two? I have 2, either head, head, or tail, tail. That's it.
Should it be 2 to the third?
I'm sorry?
I think you meant 8, which is 2 to the third.
Oh, yes. Yes, of course. Thank you. 2 cubed, which is 8. Thank you. All right. So 2 cubed and then times 2. So N of E is equal to 2 to the 4th. So the probability of E is equal to N of E over N of S, which is 2 to the 4th over 2 to the 5th, or 1/2. Okay.
I'm confused how you went from 2 to the third to 2 to the fourth.
Sure. So for the first three, I have 8 choices. For the second two, I have two choices. Is that clear?
Okay, yeah, that makes sense.
Okay, and remember last time when we were counting what we learned, chapter 5, we learned that if I'm looking at the number of possibilities, when I multiply because the 2 to the third is only a partial answer. I need the last two, and then I multiply them all together. Remember, we can add them if we're dividing a problem up into subsets, so I have a complete answer for part of the sample space and a complete answer for the other part. But I don't have a complete answer for anything in the sample space by just looking at the first 3. I need to see all 5 of them to have a complete answer. So that means multiply. Okay? So I have 2 to the third times 2. Okay? Good. The rule of complements. Remember, just as in counting, sometimes it's easier to count how many elements of something or don't have a property than it is to count the number of elements that do have a property. Okay, so if I look at an event E, and remember, an event is a subset of the set of all elements of the sample space. So if I look at that, sometimes it's easier to say what is in S minus E, and we write that as E complement. I know in sets we wrote it with the apostrophe, but for some reason in here we're doing this chapter, we do it differently. Okay, so what we know is that given an event E, the probability of E plus the probability of the complement of E is 1. Well, why is that true? Well, we know that the sample space is equal to the set, let's say, write it this way, is equal to E union S minus E. Okay, so we know that. And remember, when we were counting elements, we said the union, remember we had the inclusion-exclusion principle, and that said that the number of elements in a unit and in a unions equal the number of elements in a union is equal, in the general case, the number of elements in the first set plus the number of elements in the second set minus the number of elements in the intersection. Okay. So what does that tell us? Well, is there anything in the intersection between an event S and its complement? No, that's the definition of complement. It means that, what does it mean? It means that if something is in E, then it's not in the complement. If something's in the complement, it's not in E. So the number of elements in the intersection is 0. They're disjoint. So then we just divide through and get 1 is equal to the number of elements in E divided by the number of elements in S plus the number of elements in S minus E divided by the number of elements in S. And this, that's equals, this is the probability of E. And this is the probability of E complement. Now, in case you're wondering, why don't we just write P for probability the way they do in some books? It's because we write P for permutations. So we have to be really careful to keep our notation distinct. So probability is prob, permutations are capital P, and power set is the funny script P. Okay, lots of P's. That's why we have to be very careful to write them differently. Okay, so let's do practice problem 2 here. Okay, so here we got our red die and our green die. What's the sample space of all possible outcomes? Well, we just did this problem, kind of. So what we have is the set of all ordered pairs. Why are we going to order them? Well, the red die is going to be first, red, comma, green, where red and green are both in the set 1 up to 6. So the sample space of possible outcomes is defined by that, and the number of elements in the sample space is equal to 6 squared. Okay, so what is the probability that exactly one of the die is 6, has a 6? Okay, so what are the possible roles that can give us that solution? So that's E. E is the event that exactly one of the dice is a 6. So what are the things that can go into E? Let's look at our pairs. Well, the red can be a 6. And if the red is the 6, what are the values that can be on the green?
1 through 5.
1 through 5. So this is J, where J is equal to 1, 2, 3, 4, 5. Is that it? Well, no. I can have an I, and I can have a 6. Okay, and what are the values of I? The values of I are 1, 2, 3, 4, 5. Is there any more than that, or is that it?
I believe that's it, because there are only 2 possible spots a 6 could be in.
Very good. Very good. So how many elements are there?
10.
10. So N of E equals 10. So let's do it down here. What's the probability of E? It's N of E over N of S, which is equal to 10 over 36. Okay. Good. Let's see. I can't spell here. The sum of the dice is 5. How can we do that? Let's call that E2. What does E2 look like? I can have a 1 and a 4. I can have a 2 and a 3. I can have a 3 and a 2. And I can have a 4 and a 1. Can I have anything else? No. Can't have anything else. So how many elements are in E2? N of E2 is what?
4.
4. So here we have the probability of E2 is N of E2 divided by N of S, which is 4 over 36, which is 1/9. Okay. What about if we say the sum of the dice is at least 10? Can I have a 1 in the first position?
No.
No. Because here's E3, and that's going to be, let's see, I think I get a 4 and a 6, a 5 and a 5, and a 6 and a 4. Anything else possible? No,
5
Yes.
and 6.
I'm sorry, another 5 and 5. No, there's only one way to get 5 and 5. That's when both of the dice get a 5 on it.
What
Uh,
about 6 and 6?
At least, oh boy, you are right. We just left out a bunch. What else do we need to have? Those things roll to 10, sum to 10. Now you have to sum to 11. So you're right, we have 5 and 6, and 6 and 5 sum to 11. And who sums to 12? 6 and 6. Whew. So how many elements are in E3? So
Six.
N of E3 is what?
6.
6. Very good. So the probability of E3 is equal to N of E3 over N of S, which is 6 over 36, which is 1/6. Yes, Grant.
So why wouldn't 5 be in there twice since one could be, oh, never mind. I just answered my question.
Good. Glad to hear it. Okay. Let's do the last one first. The values on the 2 dice are different. Do we have to compute that, or can we figure it out?
I think we can figure it out.
I'm sorry?
I think we can figure it out.
You want to figure it out? Okay.
I mean, so we can try to find the number of the 2 dice same.
Well, we could do that, but I think that's harder. Well, to me,
Ready?
that's harder to me, but let's figure out what it would be here. I have 2 positions. I have an ordered list with no repetitions. What would that be? Ordered list, no repetitions.
Permutation.
Say that again.
Permutation.
Good. Excellent. It's the number of permutations of 6 things taken 2 at a time. Okay. Permutations. What is that? That's 6 factorial over 2 factorial. Okay.
Shouldn't that be 6 minus 2 factorial?
Yep. I am so glad you guys are with it today, because I seem to not be. 4 factorial. Thank you. Okay, so the probability of E2, not E2, that's not E2, that's E5. E5, probability of E5 is equal to N of E5 over N of S, and that's equal. So 6 times 5 is 30. Divided by 36, or 5/6. Okay. Now the value on the red die is less than the value on the green die. Less than, strictly less than. Okay. So what are the possible elements in E4 here? Well, I could write it, but let's say that's 1 J, and J can be 2, 3, 4, 5, 6. And then I can have 2K, where K is 3, 4, 5, 6. And then I have 3M, and then M is 4, 5, 6, etc. You all get where it is? So how many elements are in E4? Well, when the red one is 1, there are 5 elements. When the red one is 2, there are four elements. When the red one is 3, there are 2 elements. When the red one is 4, wait, I did 4. When the red one is 5, there's 1 element. And when the red one is 6, it can't be in there because there's nothing larger that the green one can be. So it's the sum of 5, 4, 3, 2, 1, and that's equal to 15. Okay, so the probability of E4 is equal to the number of elements in E4 divided by the number of elements in S, which is equal to 15 over 36. Yes, David.
So what formula will we use to calculate a number like that? Like where it's 5 plus 4 plus 3 plus 2 plus 1.
Well, we had thank you for asking that. We had a nice formula back, I think, in chapter 2, when we were talking about proofs that said the sum I goes from 1 to K of I is equal to K times K plus 1 over 2. And you had to prove that by induction. That was a problem, I think, at some point. Okay, so that's a nice formula you can use. You can go back and look in chapter 2 for different formulas for things like that, okay? Or in this case, you can just add them. It's not that many. Yes, Grant.
I don't know if this is similar to the question that David had, but I'm kind of wondering, how do we, like, is there like kind of a generic question that we should be looking for that always ends up being like that, or do we just have to solve it kind of case by case?
It's a case by case. All the examples I'm going to try and do for you are a little different. Okay, all our practice problems are a little different. So one of the things I wanted you to note here, okay, is first of all, remember probability is the number of elements in your event successful outcomes, which is the number of elements in your event divided by the number of elements in your sample space. Okay, and so we have to figure out how to count them. Now, as we get more complex problems, remember chapter 5. Don't forget it. The reason that these guys have a quiz together is that we use all the counting things we learned in chapter 5 here in chapter 6. Everything gets used. As soon as I'm done with a few more practice problems, we're going to learn some of the rules. And we had rules in chapter 5. And we're going to see how those rules transform. Now, the one question I haven't answered really, but I'm sure you can guess, is that when I talk about probability, I'm giving you fractions here. Okay. Remember, a probability of 1 means it's certain. Okay. 1 is absolute certainty. And that translates to remember, 100%. If we talk about what is the percent of chance that something is true, you say, well, if it's 100%, then it's for sure. Okay. So what happens is when we get our fraction of probability, let's go back and look at, let's pick an easy one here. 1/6. Okay. So 1/6, when I turn it in, so 1/6 is equal to roughly, approximately 0.167. So you can talk about the probability of 0.167, or you can say there's a 16.7%. Remember, we multiply by 100 to get percent chance of something occurring. Okay, so that's how we go from the fraction to the percent, and the decimal is the probability. You can talk about percent, or you can talk about the fraction. David.
Oh, I guess I forgot to put my hand down. Sorry.
Okay, good. Let's take our break. We've got 5.
Dr. Cohen,
Yes.
I got distracted and spaced out for a second. Did we finish this problem yet, or are we going to finish it after the break?
Are we talking practice 3?
Yeah.
Yeah, we haven't started practice 3.
Okay.
Okay, so you haven't missed anything.
Awesome.
Oh, Dr. Cohen,
Yes.
I just realized something, or I kind of have a question about the last part of the last problem.
Yeah. Sorry, it's
Can-
so scribbly.
No, that's fine. Can we represent all the different outcomes of the event E as a set in this case?
Oh, yeah. You can always do that. Sometimes you can't write it down because it's too big.
Oh, well, no, I meant like it has no repetitions and the order doesn't matter.
Oh, the order matters. If you write it as an ordered pair, because one is red and one is green. So if you flip it and the order doesn't matter, then you're flipping red and green, and then you don't no longer have an ordered pair.
Right. But does it end up having the same number of elements as if it was a set?
You're talking about a set. When I talked about a set, I'm talking about that kind of a set.
Mm-hmm. Okay.
So if they're ordered pairs in this set, then 2, 1 is different than 1, 2. if I look at the set 1, 2, then they're the same. And that's not the case here. Remember,
Okay.
ordered pairs have the word order in them because order matters.
Right. Okay.
Okay?
Thank-
Good.
Dr. Cohen,
Yes.
sometimes I confuse myself about whether order matters or not.
Yeah.
And an observation that I've had is that in general, if there's some way to distinguish between the objects, usually that means order matters. And if they are indistinguishable, it means order doesn't matter. Does that seem accurate? Like if they describe two dice.
Yes, if you describe your sample space accurately. So remember, when in the first case we said, you know, in the first example, we said, well, suppose they sum to 2, in which case it doesn't matter, or sum to 7 or whatever, it's sum to something. And we define the sample space as an outcome is something that sums to 2, 3, 4, 5, 6, 7. Then they're not equally likely because then we're saying that 4 and 3 is the same as 3 and 4. Okay. And that doesn't give us equally likely outcomes. So that starts out defining the sample space incorrectly. So you have to be really careful to define your sample space correctly.
Okay, thanks.
Okay, so I understand it could be confusing. So sometimes we have to be careful. Okay. Okay, I think we're on again. So here in practice problem 3, we're saying, suppose we have a class of n students and we write down each one writes down a 2-digit number. So we have n students. So I have a list of length n. Okay. Each one writes down a 2-digit number. What's a 2-digit number? We have a set A, and A is equal to 10, 11, up to 99. So how many elements are in A?
$89 or 90?
90. Good. Glad to hear it. 90. Very good. So we have 90 elements in A. And what we have is that the first person has a choice of 90 things. The second person has a choice of 90 things. All the way down to the nth person has a choice of 90 things. So the sample space is the set of all ordered lists of length. How long are they? Length n. Each element, each item in the list comes from A. So how many elements are in S, our sample space? Ordered list.
90 to the n.
Got it. Very good. 90 to the n. Okay. What is the probability that at least 2 people will write down the same number? Well, at least 2 people. Boy, that's hard. Okay. So we could work hard on figuring it out, but let's say E is at least 2 people write the same number. Okay. Then what is E complement?
At most, one person writes the same, or actually, nope,
duplicates.
no one writes the same number.
No one writes the same number. Very good. That another way of saying that is everyone picks a different number. Now let's ask a couple of questions here. Okay, I have a list of length n. What happened, a list of length 20, oh boy, I have n here, too many n's. Okay, so I have a list of length n here. What if n is greater than 90?
Then there must be a duplicate.
Good. So now let n be less than or equal to 90. Okay, now we ask the question, how do we get everyone picking a different number? Let's see, I have n, a list of length, n, all different numbers. What does that sound like from chapter 5?
Would it be a permutation?
Bingo. So the number of elements in E bar, E complement, is equal to the number of permutations of nice taken n at a time. So what is the probability of E complement? Well, that's equal to the number of things in the complement, which is permutations of 90 things taken n at a time, divided by the number of things in the sample space, which is 90 to the n. Okay? Good. Let's move on.
So, sorry, Professor Cohen,
Yeah.
are we finished then, or do we still need to find the probability?
Oh, we didn't finish it. Thank you. So the probability of E, thank you, is equal to 1 minus the probability of E complement, which is 1 minus permutations, 90 things taken n at a time, over 90 to the n. Okay, now those are both big numbers, but 90 to the n is much bigger than the number of permutations, much bigger than the number of permutations of 90 things taken n at a time, as long as n is quite a bit smaller. So that means the probability of E is pretty high. Okay?
Excuse me, so each student will write down two different numbers. So you mean the same number is like they'll write down two same number?
I'm sorry, say that again.
There here said the n of student write down a 2-digit number.
Yes.
Oh. Okay, I think I got it now. Okay, sorry.
Okay, good. Practice problem 4. This should be reminding you of what we just learned in chapter 5. Suppose that a non-negative integer solution to the equation w plus x plus y plus z equals 10. What does that sound like? What do we know that is?
Combination with repetition.
That's, I'm sorry, say again?
Unordered list.
With repetition. Very good. So it's a bag.
Bag, yeah.
Very good. So it's chosen at random. Each solution is equally likely. So S is equal to the integer solutions, and n of S. What do we know about n of S? Well, n of S is the number of combinations of 10 plus, how many is that? That's 4. 4 minus 1, 10, or number of combinations of 13 things taken 10 at a time. Okay, so those are the number of non-negative integer solutions. We don't have to figure out what the set is. We have to know what it is and be able to count it. So this has a very large number of things. We could spend all day trying to figure out solutions, but we know how to count it. Okay, what's the probability that this particular solution has W less than or equal to 2? So that says E equals the set of all elements, let's say little solutions in capital S, such that W, let's call it sub S, is less than or equal to 2. Okay. How would you solve this? Well, we could figure out. Go ahead, Jane.
Sorry, I was going to say I would partition this into cases. So W equal 2, 1, and 0. But that changes what the sum of X plus Y plus Z will be equal to, depending on each case.
Yes, it does. Yes, it does. So you can figure out exactly what that is. In this case, we're looking for the set of solutions where X plus Y plus Z equals 10. And here we're looking for the solutions where X plus Y plus Z equals 9. And here we're looking for the solutions where X plus Y plus Z equals 8. And we know how to count that. Do we have another way? Yes, the rule of complements says that I can ask the question, E complement is the set of all S in S such that W of S is strictly greater than 2. So how would I solve that way? Well, in that case, what we do is we pull strictly greater means that W sub S is greater than or equal to 3. So what we do is now we're going to pull 3 out of our solution and say W has to be at least 3. And then we're going to solve W plus X plus Y plus Z is equal to 7, because we pulled 3 out already. Okay, so this is the case of saying I have to have, remember we had a problem the other day that said we need at least 3 apples or something. Here we're saying we're solving for at least W equals 3. Okay, because in these solutions, W can equal 0 here. Let's call it W bar, no, W tilde can equal 0, but W is equal to W tilde plus 3. So if W tilde is 0, W is 3. If W tilde is 1, W is 4. If W tilde is 2, then W is 5, and we keep going, okay? So we don't want to solve that for W equal to 3, 4, 5, up to 10. That would be too hard. But we know this. So E bar, then, the number of elements in E bar is equal to combinations of, let's see, we're going to take 4 at a time, and then we have, we're going to take 7 at a time. 7 at a time. And we have 7 plus 3, choose 7, or C of 10 choose 7. So what's our answer? What's P of E? P of probability of E is equal to 1 minus the probability of E complement, which is 1 minus combinations of 10 things over, taken 7 at a time, divided by the number of combinations of 13 things taken 10 at a time. Okay? Good. I'm going to leave practice problem 5 because I want to go on here. So we have a bunch of definitions now. We're getting into more complex stuff. And we say that two events are said to be disjoint or mutually exclusive if they cannot occur simultaneously. Okay? So what we look at is we can look at the sets that those events are represented by, and that says they're disjoint if the intersection of the sets is disjoint. So for example, I can't have, if I pick 4 cards from a deck, I can't simultaneously pick 3 hearts and 2 diamonds. Okay? Can't happen. So they're disjoint. The number of events that can have 3 hearts and the number of outcomes that can have 2 diamonds when I'm picking 4 cards, totally different. 2 events are said to be independent if the occurrence of one event is not influenced by the occurrence of the other event. And we'll talk about examples of those in a minute. So we have some rules. So the rule for disjoint event, if E1 and E2 are disjoint events in a given experiment, then the probability that E1 or E2 occurs, E1 or E2 occurs, is the probability that's written as probability E1 or E2 is the probability of E1 plus the probability of E2. We're going to talk about where that comes from shortly. Now, if they're not disjoint, the same formula will work, but that says if E1 and E2 are any given events in a given experiment, the probability that E1 or E2 occurs is given by the probability of E1 or E2 equals the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Now think about sets. Think about sets. And if you think about sets, we know the number of elements in the union of 2 sets is equal to the number of elements in one plus the number of elements in the other minus the number of elements in both, because we already counted them twice. So that makes a lot of sense. Remember, we counted the numbers of elements in chapter 5. Now we're just saying, well, remember, the probability is the number of elements in the event or the union of events. If I define an event as being that something is in the first event or it's in the second event, then I have a more complex event. Then we have a different rule that says if E1 and E2 are independent events. So what's independent events? Remember, one occurrence doesn't influence the other. Then the probability that both E1 and E2 occur, that's the probability of E1 and E2, is the probability of E1 and E2. So for example, if I flip a coin, a fair coin, and I look at E1 as being the probability that I roll ahead, I'm looking at the probability that I roll ahead on the first and the probability that I roll ahead on the second. Then if I define E as the probability that in the 2 rolls, I have 2 heads, okay, then E1 and E2 don't affect each other. Okay, because they're independent. What I roll on the first time doesn't affect what I roll on the second time. So the number of events, the number of outcomes in E1 and E2 is equal to the number in E1 times the number in E2. Okay? Think about sets. Okay? Good. So let's look and ask which problems are disjoint here. So we're going to roll a coin, toss a coin 4 times. Okay. E1 is the event that there are exactly 3 heads, and E2 is the event that there are exactly 2 heads. Can they both occur? Do they have an intersection? No.
No.
So they are disjoint. So now if I choose 4 cards. E1 is the event that the cards have the same value. And E2 is the event that the cards have the same suit. Can they both occur at the same time?
No.
No, that's right. Because if I have 4 cards of the same value, then I have 1 of each suit. If I have 4 cards in the same suit, then they have 4 different values. So they're totally disjoint. Now, when I choose a committee of 3 people from a club that has 8 men and 12 women, if the E is the event that the committee has a woman and E2 is the event that the committee has a man, are they disjoint events? No, they can both occur. You can have lots of committees that have 2 men and 1 woman, or 1 man and 2 women. So there's nothing that says that they're disjoint events. They can occur in one solution, in one outcome of 3. You can have both. So they are not disjoint. Okay, let's do an example. The general sum rule. I'm going to leave this for you to look at if you haven't already. This just looks at what we talked about already. It follows from the set theory. If I look at the set of events out of the whole sample space, remember, we're taking subsets of events, and we're asking if the subsets that represent the 2 possibilities are disjoint or not. Okay, and what is this? Where does that come from? That's the principle of inclusion exclusion. Okay, remember, when we're doing probability, we have to count the number of elements. The number of elements. So if I say, how many ways is it possible to pick a king or an ace? They're disjoint. E1 is pick a king. E2 is pick an ace. Okay. So what is the event E? The event E is to pick a king or an ace. And that's going to be the probability of picking a king plus the probability of picking an ace. But if I have an example, how many ways is it possible to pick a king or a heart? They're not disjoint. Okay, because one of the kings is a heart. There's something that's in both solutions. Okay, so there are 4 ways to pick a king and 13 ways to pick a heart, and 1 that's in both. Okay, so if I ask, pick a king or a heart, that is my E, and E1 is pick a king and E2 is pick a heart. Okay, good. So we have another practice problem here. A card is drawn from an ordinary deck of 52 cards. What's the probability that the card is an ace or a jack? Ooh, okay, E1 is pick an ace. What's the probability of picking an ace? What's the probability of picking an ace? How many ways can we pick an ace? There are 4 aces in the deck, 52 cards, 4 over 52 or 113. E2 is the probability of pick a jack. Okay, probability of E2 is, well, how many jacks are there in a deck? There are 4. How many cards? 52. So our probability is again 1 over 13. So the probability of picking probability of E1 or E2, well, are those events disjoint? Yes. Aces and jacks are not the same. So that would be 1 over 13 plus 1 over 13. What's the probability that the card is a heart or an ace? Well, what's the E is E1 is an ace? Pick is an ace. Well, if the pick is an ace, then we know that the probability is 1 over 13. What E2 is pick a heart. What is that probability?
1 over 4.
1 over 4. Very good. E2. So now, what is E1 intersect E2? Or E1 intersect E2, which is E1, if it's E1 and E2, we can say that. So we need something that is an ace and a heart. Is there anything that's an ace and a heart? Yeah, there's one of them. So that's one, the probability of E1 and E2 is 1 over 52. So this is number 2 down here, number 2. So the probability of E1 or E2 is equal to the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Remember, the minus comes in because we already counted that in there twice. So we have to take off one of them. So that's going to be 1 over 13. No, yeah, 1 over 13 plus 13 over 52 is 1/4 minus 1 over 52. And I'm going to leave part 3. Part 3 is harder because here we're going to divide it into 3 events. E1 is diamond, E2 is a club, where E3 is a king. And we want the probability of E1 or E2 or E3. And to do this, I'll give you the hint. You have to go back and look at the principle of inclusion-exclusion for 3 sets. Okay? Because now that's how we have to compute it. Yeah. Okay. So now let's ask the question. Let's ask the, well, I won't ask the question. We'll start here next class, but we'll call it practice problem 1 next class. Are there any questions or anything anyone wants to ask me before we end today?
Can we use the union and intersection signs when we're doing these kind of problems?
No, because you're not looking at a union, you're saying or. The word, what you're doing is looking at the sets to get the number of elements, but when you're looking at events, you're saying or. So get into the habit of doing it. I know it's hard, but you know, when we talked about equivalencies, remember we talked about logical equivalencies, set equivalencies, and Boolean equivalencies, and they each had different symbols. And you had to use the right symbol when you were talking about the right one, even though there were equivalencies among them. So this is yet another one to learn the right, or remember in Boolean, it's the same idea, or you can think of as plus is union, kind of, and is times is intersection. Okay, so think about it that way, but they're different. You're thinking different things. Okay,
Just to be clear, we would just write the word and or the write the word.
absolutely.
Okay, thank you.
Anything else? In that case, I will see you next